So let me give you the little bit agenda of our webinar actually. So let me start with again. So we will start with little introduction about myself. Then we will have the little intro about artificial intelligence. Maybe everybody knows about it or some person knows about it. Then we will have the kind of the data which we use for the type 1 diabetes prediction, and what is the problem statement actually which we are solving, and AI tool which we have used, and which model which we have used, and the selection of the model. And definitely at the end we will have the Q&A session actually. So let's begin with the webinar. So myself, Reenal, basically I am from India. So I have been working with an IT industry past 7 years. So I've been initially with the backend development and 2+ years of experience as a data scientist. So I have worked with a couple of organizations with India as well as with Sweden. So some of the portals which my success stories were published, and it was the WITS Pune and definitely the iNeuron, where I started my data science journey. And also I am an open source contributor, so I contribute to the various open source library like TensorFlow and all. And like I've been a mentoring the few students, like the college students, to be transitioned into the data scientist. So apart from overall work, so I like playing the cricket, traveling, and the cooking. So this is all about myself actually. So let's start dive into this. So a little intro about mainly AI. This is where I work, and it's a company, and personalize and optimize using the AI actually. So we are actually the AI stores actually, where we store the knowledge object and where we share the knowledge object. So the knowledge object can be the any kind of the findings and the patterns, or it can be the data source. So we store, we share, or we can do whatever with that knowledge object. So this is, so we can share Miranda, or we are doing what we are creating is an AI stores at a mainly AI. So this is what exactly the short intro about our company. Then let's start about the artificial intelligence. So many of us know actually, basically artificial intelligence is the ability of the machine to learn or adjust the experience based upon the past data, or the ability of the learn the pattern based upon the previous data. So that's what then artificial intelligence look like actually. It's a popular branch of the computer science, which aims to build the intelligence machine capable of performing the human-like tasks. So actually, so as a human, we are making some decisions. So how we are making the decision is based upon the past experience, the past data which we have. So that's what the pattern which we are actually following with this kind of the algorithm or in a AI. So this is how the AI progression look like actually. So this is just a basic intro about the AI and all other stuff. Maybe you guys all know actually. So initially AI started with 1950. So it's like a early stage of the AI where we just having the statistics and all other stuff. Then 90s, 18, 19 we have started with the machine learning. In early 20s we have started with a deep learning. So this is the progression look like with an AI actually. So if you see, AI is a branch of it's a field, it's combining lots of stuff. So we have the machine learning, computer vision. So computer vision, machine learning, and deep learning, it's a part of the AI. So each has its own benefits and each has its own structure. So we have the machine learning where we have the supervised and unsupervised unsupervised different types of an algorithm. And this is a part where machine learning domain or machine learning, this actually the blue circle represent actually the computer vision part, which focus on the image processing, which deals with the image data actually. Natural language processing or the speech, which focus on the text and the text data mostly. So this combine everything into the AI actually. So the machine learning, so algorithm that automatically learn using the training data and improve the experience without explicitly programming. As I mentioned, So we have the couple of algorithm where we feeds the data and past of the previous experience or the past of the previous patterns. So that improves the prediction actually, that improves the experience of giving the decisions actually. So that's what about the machine learning. Then we have the supervised machine learning algorithm where we have the label data actually. So for example, we have the categories like, so for example, human, like for example, the house price prediction based upon the some features. So house price prediction, price of the house is the label data. So we have the label and unlabeled data. So unsupervised machine learning where we don't have the label data, we just predict the pattern. So for example, in unsupervised machine learning, we just cluster the data based upon the similarity. So we cluster the data, like for example, like the male data together or the female data together, or we cluster the data based upon like the sales in the particular area, something like that. So that's come under the supervised machine learning algorithm. Then there is one part part where reinforcement learning is also there, where we don't have the much training data available. So that's reinforcement loop is going to be there. Like we panelize the each faulty actually the prediction. So that's the reinforcement loop which we are going to have. So that's another topic of the machine learning. Then we have the deep learning actually, where we have the neural networks, where we have the neural networks. So deep artificial intelligence, we have the different layers of the network, so which we mimic the human like the brain actually, so that we combine the different layers to get output, predicted output. So that's what the deep learning algorithm look like actually. So basically this is what is an agenda, to just a quick give overview of this, what is machine learning and AI and all other stuff. So let's start about the TEDdy. So what we have, we got in the TEDdy in the data. So TEDdy is actually what I can say is study conducted in Sweden and the USA, where they are collecting the child's blood data actually from 0 to 15 years actually. So each 3 months they are calling the child and they are collecting the blood sample, and from the blood sample they are collecting the data. So that can be the data of the various parameters like hemoglobin of the child, the environmental, how the child lives, and there is the C vitamin, B vitamin data, so or the HLA data. So these all type of the data from the blood they are collecting from 0 to 15 years. So this is the study conducted by the TEDdy, and that's what the data which we have got, and that data is stored in a NIDK. So from where we get this data. So the general idea of the study is to identify the TEDdy study, or why they are collecting this data is to identify what's exactly triggering the type 1 diabetes actually. And what is it the blood? It is something in the blood, or it's something in the environment, or what exactly overall is triggering the type 1 diabetes. So identify such kind of the factors. So that is some of the focus of this collecting the data actually. The participants in the study is followed till 15 years, and participants are no followed and once they reach the end point. So end point of the study is 15 years, and the participant they are no longer follow once the participant is diagnosed with a type 1 diabetes actually. So let's suppose the participant diagnosis with a type 1 diabetes at a 4 year of age. So they are not going to follow afterward actually. So this is a kind of the data which we get actually. So let's talk about the type 1 diabetes actually. So type 1 diabetes is a complex autoimmune disease actually. So resulting in the destructing in the beta cells actually. So which leads to the deficiency in the insulin production actually. So there is some kind of the proteins which kills the beta cells, and that beta cell deficiency actually leads to the deficiency in the insulin. So that's what an autoimmune disease is called. And definitely the diabetes is a worldwide epidemic. And it's estimated 382 million people living with a diabetes in 2030. But by the now, is the number is definitely going to raise actually. So the prevalence of the type 1 diabetes individual at younger age has an increase by the 23%. So what has a study or overall research with related to this type 1 diabetes? So the people are sense like in the younger age, people are having more 20% more diabetic than the older age. So that's what the study says actually. So this the statistics report says actually. Then the study researchers believe like the T1D triggers is by the environmental factors. So there is some factors in the environment or the bacteria or the ground or the climatic condition or where the people live, or if that child or the patient live with a animal or such kind of the pet. So there are other environmental factor that leads to the triggering point for the type 1 diabetes, or there is some genetic factors which leads to the triggering point for the T1. So we have found like there is we have the main association with the T1D is an HLA, which is a genes actually. So in human body there are different kind of the genes which we present. So the particularly if the person having this kind of the genes actually like the DRT, DQT, DR4, DR8. So if the person having this kind of the genes, that having the probability that more chances of getting the T1D. So the person falls under this category. So that's chances of having the getting more type 1 diabetes. And these are the antibodies. So for the each time child visit for the collection of the data points, so they perform one test actually, so that they check if that particular antibody was present in that in their blood or not. So what kind of the antibody? So ICA, IAA, GADA, zinc antibody. So these are all the antibody which tells like these are the triggering point for the T1D actually. If this antibody was present in the blood, means definitely that person is going higher risk of having the diabetes actually. So these are all factors and something related to the T1D actually. Now, what is our current problem? So with all this data set, the blood sample data set and the antibody collection, each month they are collecting the blood, they are testing if the person is having the antibody with all other data. So with having that data, what is the problem statement we are solving actually? So we want to have the probability of whether the person is detecting the diabetic or not, and when is that person is going to have the diabetics, both. So this is the problem. So when and what, if having or not, and when is going to person is going to develop diabetes. So this is our current problem statement which going to we are focusing actually. So that's what we have been focusing, and the tools which we have used till now is definitely the scikit-learn. This is a famous machine learning library for the processing and the where we have the different machine learning models. So definitely we have used the basic scikit-learn, the lifeline library which we use for the survival analysis, and the pandas and numpy for the pre-processing of the data. Definitely if we need, we use the TensorFlow, and definitely we use the GitHub for the versioning control, and we use the Visual Studio and the Jupyter Notebook for the coding and all ID. This is we use for the coding purpose. So that's what the tool which we have used. So let's here is a general workflow for basic problem statement which we have defined how we are going to solve. So first we acquire the data from the NIDK actually. So that's the data which is present in the 53 different files. The data was very much unstructured. So the data is spread between the 53 different files actually. So it's not a one file which we got it. So we have the 53 different files actually. So we process the data, we drop some of the data. So we encode the data. So we input the data, then we train the model, and then we visualize. So this is a general workflow which we want to follow. So as I mentioned, so TEDdy consists of the 53 different files. So we use these 3 files for this particular experiment, which is the 3 months interview, TEDdy update form, and the test result, and the diabetes diagnosis. As I mentioned, so in each file, there are different variables which is present. So we want to capture that variable. So we use in test result, we have the information about the GAD antibody, if that is present or not. And in diabetes diagnosis file, which we have the information about if the person is with a T diagnosis with a T1D or not actually. So that information is which we are having in this file. So we have analyzed the 53 different files, and we, for this particular experiment, we realized like the 3 files which is most important, and we should start with these 3 files, and we imputed, and that is what we have started with this 3 file actually for this particular experiment. And we imputed the data with a mean. Some of the features we imputed with a median, some of the features which we imputed with a mode. So for this particular experiment, which I written here is a Kaplan-Meier experiment. So for that particular experiment, the data which we look like is we want to have the data is in this form actually. So here is the T1D and the survivals in the days. So before we go into that experiment, I want to give the little bit introduction about the survival analysis. The survival analysis is a time to event analysis actually. So for example, if I give the treatment to the particular person, what is the time, how long that has been survived before actually happened, before that person has going to have that event actually. So maybe the death or something actually. So if I give the treatment with respect to the cancer, the event is in terms of this when that person is going to have the cancer. So everything related to the event to time analysis. So event is an experience of the interest which we have, we want to observe or we want to be see. So here our event of the interest is a type 1 diabetes actually. And so when we talk about the data, so we in that data, all the person is not going to have or experience an event. So it's not going to, it's like every person is going to experience the type 1 diabetes in event actually. So each person is not going to have the type 1 diabetes. So that kind of the observation, which is called as a censorship observation actually. And so Kaplan-Meier graph, which is called the survival probability graph, actually survival probability is the probability which is the probability of the past anytime t actually. So I just want to show you that this is an survival model, Kaplan-Meier graph actually. So Kaplan-Meier graph, which in the x-axis is the timeline and the y-axis is the survival probability. So this is a graph which we want to plot and that is given by the Kaplan-Meier graph, which is a non-parametric model. So for this model or for this graph to get, so what is we need to feed is a two parameter which we need to feed. How long that person has been followed and if that person has been experienced the event or not actually. So before that, let me tell you the feature or like the feature of this survival graph or the Kaplan-Meier graph. So if you see here, as the time increase, the probability of the person of getting the any kind of the event here with respect to the T1D is decreased. So as the time increase, the probability of the survival with respect to the any kind of the event is definitely decreased. So we definitely have the curve which is falling over the period of the time. So what I'm here explaining here, so on the x-axis we are having the timeline from the 0 to 120, whatever the period which we are going to follow that, and on the y-axis we are having the survival probability. So from the graph property, if you see here, as the time increase, the survival probability is going to be this. This is a property of the Kaplan-Meier graph or the survival function actually. And the survival probability of at the time t is definitely higher at the time 20 is definitely higher than the survival probability at the time 80 actually. So these are the properties of this Kaplan-Meier graph and the survival function. So that is what
Ma'am, it's
yeah.
just a request that as everybody lost the part, can you please re-explain the same thing?
Okay,
If it
okay.
is possible. Yeah, thank you so much.
Yeah, sure.
Yeah.
So our experiment. So let me go back to the slide actually. So we are planning one experiment. So where we want to plot a survival curve, which is a Kaplan-Meier curve actually. So the Kaplan-Meier curve which we want to plot, and that is how it's look, which I want to show in this graph actually. So in this graph, which is the Kaplan-Meier graph actually. So on the x-axis we are having the time, and on the y-axis we are having the survival probabilities actually. So this is a properties of the survival function and the Kaplan-Meier graph actually. So as the time increases, the survival probability is definitely going to decrease actually. So, and the survival probability at time 20 is definitely higher than the survival probability at time 20, at time 80. So this is the general properties of the Kaplan-Meier graph and survival function. And this is what we want to, this is what we want to plot actually. So let's go back to the slide. So this is what the experiment which we want to plan actually. So we have started with this creating the data set where we having the two features. So where we having the one feature 8,600 data point. Two feature we are having, which is the survival in days and the T1D. And in that data frame, we are having 8,600 rows, which is a unique data point. And out of these, 333 developed the T1D and 8,300 which is not developed the T1D. So this is just a two feature I'm having in my data set actually. You can say the two columns of the data frame or the two column in the Excel file. The survival in days. So for example, one person, how long it has survived from not getting T1D. So 500 days, 600 days, 700 days, as it have get the T1D or not. So this is the general data structure look like. So now let's understand 561 days. So we are having 1,568 people who is not diagnosed with a T1D and 80 people which is diagnosed with a T1D. So from 561 days to 1,772, 643 people which is not diagnosed with a T1D and 49 people which is diagnosed with a T1D, so and so forth. So if you observe this column 1, 18, 49, 47, 46, so that event of happening is not constant. So it's not changing by 5 times. So by 15, 30 or 45. So it's not changing with any type of the constant. So it's happening randomly. So it's not the event happening is random at a time. It's not a constant. So if you look at the distribution, so this is a distribution of the survival in days actually. Okay. So that tells us the randomness of the survival days in the distribution of the days actually. So we feed this data. So whatever this data we have feed to the Kaplan-Meier graph, which takes a two parameter. One is a survival in days and another is what is an event which has happened. So when we feed this data, we get this Kaplan-Meier graph and the survival function. So this is a graph which we get when we feed that to the Kaplan-Meier function actually. So like if you observe this graph actually, so here is a survival in days and here is a probability. So we have the data from 0 to 5,000 days and survival probability from 100 to 90. So if you see, as I mentioned, the survival probability dropped from 100 to 92% actually, as its days changing from 0 to 5,000. As days increase, the survival probability is going to definitely going to decrease actually. So that's the general tendency of the Kaplan-Meier graph, which is a non-probabilistic model. So that is what we have used. And Kaplan-Meier graph we can use to check the probability between the different group actually. So in the data, so I can feed the, I can use this data, or I can use this graph to plot the graph between the different group actually. So so if you observe this actually, so blue line is the data for the female, and the so the orange line is the data for the male. So we plot the graph survival function for the both, like male and the female. So from this graph, if you see, both the probabilities going in a similar way. There is no difference between the probabilities. So from this graph, which we can observe. But from this graph, this is an interesting observation. So we are having the one group actually. So where we are having the one group where we have zero actually. That's group is the family with not T1D, and one group is a family with a T1D, and the second group, which is a green group, the family which we don't have any data actually. So from this, definitely we see the yellow line, which is a group one, the family with a T1D. So if some person having the family history with a T1D, that definitely the survival probability is less than the family who is not having T1D. So we can see from this graph actually, the family with a T1D, the survival probability drops drastically actually. So it's dropped from 100% to the 92% actually. So these changes we can see from this Kaplan-Meier graph, survival graph, and we have checked with another different groups actually. So there is the number of the antibodies positive. So if the person having the 1 and 0 antibody positive, 1 antibody positive, or the 2 antibody positive, or the 3 antibody positive, or the 4 antibody positive. So we can see the purple line, the person who is, these are the different group, or the group of the person who is having the 4 antibody positive. Definitely their survival probability is less than with respect to the others. So it's dropped till 80% actually. Their survival probability dropped till 80%. So the survival probability of the person who is having the 4 antibody positive is definitely less than the person who is not having any of the antibody positive actually. So this is the comparison. So from this graph we can learn, or we can see how we can compare between the two groups actually. So if suppose so with the Kaplan-Meier graph, or with this survival function, so what we can see, like if suppose we have given the treatment for the female and we have given the same treatment for the male, if there any change, is their survival probability increase or decrease? So with this kind of the graph, we can check that actually. So this graph helps us to compare between the different groups actually, and so that is the aim, to look on different groups, how different groups are performing. So we can give the special attention to the particular group where the survival probability is dropping. So from this graph, we can see the person who is having the 4 antibodies positive, their probability is definitely less. So I can see what we can do with that particular group. Actually, we can give some special treatment, or we can give some special vaccine or something, so that they can survive longer. So with this help of graph, we can compare, or we can see how we can do with the different groups actually. Similarly actually, let's say the child, if the child is spend time with a smoker actually. So 0 is a group where we don't have any information, and 1 is a group where the yellow line, which the child spend time with a smoker, and green is a group where child don't spend time with a smoker actually. So from this group, if you see the line, the yellow line is below the blue line actually, the green line actually, the yellow line, which is the times not spent with a smoker. So definitely their survival probability is less than the time who has time spent, the child who spent time with a smoker. Actually, the green line survival probability is greater than the yellow line. So from this, we can say if the child spent time with a smoker or with a non-smoker, how their survival probability change actually. Okay, now so we have checked with this different group to sense how different groups are performing. So with the mother first child also. So if the particular child is a mother first child, how is the survival probability changes with respect to if it is their second child or the third child. So 0 is the group where we don't have any information, and 1 is a group where the child is not a mother first child, and second is the group where the child is a mother first child. So it's definitely the green line, which is the mother first child, that survival probability increase. If the child is the mother first child, then definitely the survival probability is greater than the if that child is a second child or the third child actually. So in that way, we can compare and we can see in that way this Kaplan-Meier function, which is a non-probabilistic model, which help us to compare between these two groups. So this is what the results which we got from our data. And so let's say this feature where we having the two antibody actually GAD and IA. So these are the two antibodies. So if that is present or if that is not present, so that's they are actually checking in each 3 months if that antibody is present in the blood or not present in the blood. So if these two antibody was present in the blood, so definitely their survival probability is definitely going to decrease. So that's how its graph is showing actually. And these are the combination of other antibody GAD and IA2. If these two antibody was positive or it's present, their survival probability is decreasing. But how it is decreasing? So it's decreasing from 100% to nearly 90 to 90. But if you see if GAD and IA, that antibody is positive, their survival probability is drastically decreasing actually. So we can observe, we can sense from this graph actually. Similar with these two antibodies. So if these two antibody was present or not present, how these two groups are performing. So definitely if the person who is not having the antibodies, definitely their survival probability is higher than the person who is having the antibody. So this is with respect to the Kaplan-Meier graph, basically. So this helps us a lot to check between the different group and to perform this survival curve. So if you want to plot this survival curve, we just want to give the two variables, how long that is survive and the event of the influence. These are the two parameters which we want to pass into this Kaplan-Meier graph, and that is available in the Python Lifeline package actually. So that is available. Then we have check with the Cox proportional hazard model. What is this Cox proportional hazard model actually? This is a semi-parametric model which solves the problem of the incorporating the covariant actually. So suppose we are having the different variables. So suppose the HLA, HbA1c value, or there is genes data. So how that is affecting to the survival probability? So is whether the age is affecting more, or whether HLA is affecting more, or whether the HbA1c value is affecting more. So what is the variable, or which variable is affecting more to the survival probability? We just don't want the survival probability, but we also need the information, like whether the height is affecting more or the weight is affecting more to the survival probability. So that's what we get from the Cox proportional hazard model actually. So it's a semi-parametric model. So general workflow for Cox proportional hazard model is definitely acquire the data, process the data, drop the data, encode the data, And we use the imputation method is definitely the median for the sum of the feature. And we use the feature selection techniques where we use the Pearson correlation, chi-square methods, random forest. So these are the feature selection method which we use. So definitely we want to use the feature in an experiment which is definitely correlated with a dependent feature. We don't want to use all the features. So that is what we did in the feature selection step. Then we use this model to fit and predict. And these are the model evaluation parameters. So with respect to the Cox proportional hazard model, so these are the AUC concurrence index. So these are the model evaluation parameters. As long as if you know in the machine learning models, so we having the classification report, classification table, and we are having the R square, adjusted R square, mean absolute square. These are all the model evaluation parameters. So, but with respect to the Cox proportional hazard model, these are the model evaluation parameter which we have it. And the interpretation of the model is definitely with a p-value and the hazard ratio. So these are the basic workflow which we design. And we follow this workflow until we get the best model evaluation result, actually, the concurrence index or what we want to achieve, or the AIC. So if you have a good AIC score, definitely. If not, then follow these steps actually. So that's what the basic workflow we have followed. So as I mentioned in the tidy, we are having the 53 data files. So the data is an unstructured. So this data processing pipeline which make the data in a structured way. So this is a structured data which we have formed. And while making the structured data, so these are the files which we have used actually. And so if you look at this right-hand side table, so we are having, so we make a structured data where we are having the 8,643 entries and we are having 22 columns, 22 columns actually. So AB positive. So these are the columns I will explain in the next slide. So in that 8,640 data point, so 333 was developed with the T1D and 8,307 which is not developed with the T1D. So that is a general data which look like. So let's understand what each feature is actually tell us actually. AB positive, so the number of antibody positive actually. So whether the child has a one antibody positive, 2 or 3 or 4, or it does not have any antibody positive. So that is this feature tell us first antibody positive. So out of this 4 antibody, which was the first antibody was positive, whether it's a GAD, IAA. So this feature tell us that information. And GAD, I and was based. This feature tell us if the GAD and IA antibody both pair was a positive at a first or not. Out of this four pair actually. So if this pair was a positive first, then this is 0. If this pair was a positive, if not, then this feature was we mark as a 1 actually. So if this antibody pair was positive, then we mark as a 1, and if not, then we mark as a 0. So that is what this feature represent actually. Basically, we check if these 2 pair of the antibody, whether that is positive or not. So that's just a categorical variable which we have created. And definitely then we have the gender, then we use any of the family member, that data we use, then DQB2, which is an HLA category, which HLA category that child belongs. So that is the data which we use. This is a second HLA category. So that is this is a feature also which we use. Then the child parent status. So whether the child is married, so the child parent was separated, or child parent was is in living, or is married. So that status which we have used. Then we use the feature which is a child spend with a time with a smoker or not, and where does the child lives, whether the child lives in a farm or the city or the village. So that's the feature which we have used. the parent, the how many time the parents has visited the child if it is separated, how many rooms was the child lives in, where that's how is the child live, so whether that is affecting to the T1D, so whether child lives in a 4 rooms, 2 rooms, or the 1 room, so that is a feature which we have included. Then we are having the vitamin C data, then we are having the vitamin D data for the child, then the length of the child, then weight of the child, then definitely this is a target variable, child is positive with a T1D or not, and the survival index. So this is what the data which I have, this is the features I have explained, and this is how the structure data which we build. So data, definitely the data, making the unstructured data to the structured data, there is a data processing pipeline. So where we merge, we drop the feature, where we combine, where we fill in with the missing data. So these are all the processing which we do for getting this structured data. So then we perform with the Cox proportional hazard model. So this Cox proportional hazard models will give us the p-value and the hazard ratio. So these are the results. If you look at this right top, this table, so that is the results which we got from the Cox proportional hazard model actually. So the hazard is essentially the inverse of the survival probability. So it basically tell us how rapidly that subject is getting T1D, how rapidly that subject is not. So survival probability is telling us how rapidly that subject is not getting T1D, but hazard is telling us how rapidly that subject is getting T1D. So that is the inverse of hazard, is definitely the inverse of the survival. Then the hazard ratio is the ratio of the rates corresponding to the condition described of the 2 levels of the explanatory variable. For example, the drug study, the treatment of the population may die at a twice rate per unit of the control population. The hazard ratio will be 2, indicates the higher the hazard of the date of the treatment. So it's basically the ratio, like whether ratio between the 2 groups actually. So if the group 1 where the treatment is given and the group 2 is not, treatment is not given. So that's basically the hazard ratio, the ratio between the 2 groups actually. So here I can say, let me little bit zoom in if you able to see. So this is the table which I want to discuss actually. So these are the features which we have taken. So what is we have to see is the p-value. So p-value is less than 0.0.5, means that feature or that variable is the definitely more dominating or more interesting to look upon actually with respect to the target variable. Our target variable is definitely the, we want to see with if the child has developed with a T1D or not. So these are the significant variables. So if you see our AB positive, first AB, the GAD-I, and so these are all significant variable which we have observed from this p-value actually. Now so from this table or from this result, so we have observed that AB positive, first AB, GAD-I positive, GAD-IA, and GAD and zinc, and IAA, IA2A. So these are highly significant variable with respect to the T1D because since it has a high p-value. Now the AB positive is the significant coefficient is 0.04. So its a coefficient is 0.04. So if you see here, the p-value is definite, is fine, is less than 0.04. But what is the coefficient is 0.44. And we interpret 1.5 is a hazard ratio. So if you see here, the exponent of the coefficient is a hazard ratio. Like if you see exponent of the 0.04 is a 1.54, that is a hazard ratio actually. So we having the patient that is AB positive, the instances hazard ratio is given by, so 1 minus, so 55%. So we can say the person with the AB positive and the person, so person with the AB positive has a 55% chances of getting T1D. So that is how this hazard ratio and p-value and this results, how we interpret this result actually, how we use these results actually. The similarly with the first AB positive, the coefficient is a 0.21. So is interpreted as e raised to 0.21 is 1.21 is a hazard ratio. So, the person with the first antibody positive is 23% more chances of getting T1D than with a person who is not having first AB positive actually. So this is how we interpret this p-value, coefficient, and the exponent actually. Now, as we have seen, the hazard ratio indicates how much the baseline hazard change due to the 1 unit change in the corresponding factor. So as I mentioned, how is the, if I give the treatment, what is the change with respect to not given treatment? So that is the ratio of the change is given by the hazard ratio. So if you see hazard ratio is 1 indicates the no effect. So if we have got the hazard ratio 1 means that indicates the no effect, whether we have given the treatment, not given the treatment. If we get the value 1 means that treatment is definitely no useful. So but if the hazard ratio is greater than 1, so indicates that the hazard ratio as covariance value rise, indicates that a decrease in the hazard ratio. So if the hazard ratio we got is greater than 1, that indicates the whatever we have given, so that tends to increase in the chances of getting the T1D. So if the hazard ratio is less than 1, that indicates the chances of decrease in the T1D. So that's the general interpretation of the hazard ratio. Here is a partial likelihood is partial. If you see from this table, so we get a concurrence index and the partial likelihood values also. So partial likelihood values of the model, what we get is a minus 2382.10. This is useful to compare the model goodness of the fit with a different version of the same model. So we can run the same experiment with a different feature and we can check the more partial likelihood value. So that is the, so we can use this model evaluation parameter, so we can check between the different models. So so higher is a partial likelihood values, definitely the goodness of fit is good. And another model evaluation parameter is a concurrence index. So C index, that is gives the probability of the randomly selecting the patient who is experiencing the event has a higher risk score than the patient who is not experiencing the event actually. Determine the means that you're able to say the high reliability between the two patients, which one is a shorter survival time actually. So actually the concurrence index is somehow similar to the ROC curve. So definitely the higher is the concurrence index, so the area under the cover is a more. So definitely we can say the model is good if we have the higher concurrence index. So if we have got a concurrence index which we between the 0.5 indicates the poor model. If we got a concurrence index over the 0.7, which indicates the strong model. The value, if we get a concurrence index 1, which means the model perfectly fits to the experiment and will certain out and will who will give the experience certain outcome. Means that's the best model if the concurrence index is. So we will actually in practically we want to get a concurrence index between the 0.7 to 8 to 9. So that is the model evaluation parameters for the Cox proportional hazard models actually. And as of now we get concurrence indexes, if you see 0.94. So let's see here the last data. So we have taken the 5 data points. So let's see the zeroth row. So zeroth row where we have the data for the AB positive, first AB, GAD IA positive or negative, GAD IA 2A positive or negative. So this is the zeroth row for the first patient actually. So if we want to get a survival probability for the first patient, we can get it. So if you see, so we can get a survival probability for the each patient and we can tell us what happening for that particular patient and at what exactly time. So let's consider this 0 patient, which is at a blue line. So if you see the blue line actually, so actually it's merging to the red line. So let's consider the purple line. The purple line is a 79 patient actually, the 79% actually. So if you want to tell what happening to that 79%, the purple line, if you said at 4,000 days, the purple line, what is the survival probability of not getting T1D is 98%. So from this survival curve, we can tell what is the survival probability at what time. So this is what we can get for the each of the patient actually. So this is what about the experiment, and this is what about the data, and this is what about the short webinar which I want to give. So we can take us some of the question. If can you take one by one question actually? It will be helpful.
Okay. So I'm just focusing on the questions that were placed on the Q&A section. So Pavan Gadde has asked, how did you arrive the bins for days? And he wanted
How
to
do
understand the approach for binning.
binning? So this may be right. So this right.
Yeah,
This
kind of.
one right. So this is a general distribution actually. So we can get it from the distribution actually with a Python course. So definitely. So we just check what is how that we just count how much number is there bit for the 0, 1 bit for that particular interval. So we have taken this interval. So we see what are the number of 0 and 1. So event happen and not event happen. So that's what we just get this actually. So it's just a normal distribution which we have plot actually.
So,
And this distribution, so this is a distribution for the survival in days actually. So this is not a distribution for the 0, 1 or the event happen or not. So this is a distribution. So each patient has a data for how long it has survived, or we don't have the data for the how long it has survived. So that data is what a survival in days it tells us. So that features distribution is what it's look like actually.
and next up we have Abhijit Batra. He asked,
Hmm.
how did you deal with imbalanced data class?
Okay, great question actually. So yes, so definitely we are having the data which we are having is an imbalance. So we are having the more of non-getting T1D than the T1D actually. So definitely we use some of the strategies to balance the data. So definitely for balancing data, we use the upper sampling. We use the we use the upper sampling method. Definitely. That's a basic method which we have used. So we sample more number of the events happen. So so there are the two class. Class is a 0 class and the class 1 is a class. Let me tell you, there are the two class. One class is a class where the people is not having type 1 diabetes. Class 1 is the people who are having type 1 diabetes. So this class data we are having less. So we just upper sample them to get the balanced data actually.
Okay. And next up we have Edward. He asked, what is the Python package for KM and CPH?
So Kaplan-Meier graph. So for Python package, so for this kind of the graph, so as I mentioned, so let me so this Kaplan-Meier graph which I have shown you here. So we use the lifeline actually. There is a Python package called the lifeline actually. So we can use that graph Python package to get this graph actually.
Okay. And how do we extend and estimate the survival probability of a new time period?
New time period. Okay. So let us okay, new time period. So let us look at this patient 79 actually. So 79 patient has this data and we have plot the survival curve. So which we saw in the purple line. So if we want to know what is the survival probability at 300, so we just go here and So top with respect to the y-axis. So if you see here, the 98%. At 400, we are having 95%. So this is how we can get it for the individual patient, actually.
And the survival in days feature included two numbers. How derive time, like in the x-axis, from those two numbers? I didn't get the question.
Can you tell us again question?
Yeah, the question is somewhat like the survival in days feature included two numbers, and how to derive time in the x-axis from two numbers.
Survival in days feature does not have a two feature actually. That's a one feature where we having the, so for example, let me tell you what is the survival in days, that feature. So that feature, so like a patient one has survived till 500 days. Patient two has survived till 800 days of not getting T1D. Patient seven has got T1D at 1000 days. So that is what a survival in days actually, that data actually. We have the data for 1 to 8,640. So the first patient may be survived till 2000 days. Second patient may have survived till 5000 days of not getting T1D. Third patient has got T1D maybe at 3000 days. So that is what a feature represents. Okay, thank you. Thank you for patiently listening. I hope this maybe it's not a deep dive, but at least some of the basic overview, highlight of the overview, what kind of the data which we have and what is the comparison which we do. So I hope that is audience will get and get that knowledge and enjoy this session actually. Thanks for having me on the webinar actually.